Evening, ladies and gentlemen. Welcome to the Moncure Conway Memorial Lecture. These lectures have been going on since 1910, with not many interruptions. There were a couple during the Second World War, although in fact there were occasions on which lectures were held here. You'll be very pleased to know that during the course of one of them, a bombing raid occurred, and a local church nearby was bombed, but not Conway Hall. Well, it's been a series of lectures by some amazingly distinguished people in the past. Bertrand Russell, A.J. Ayer, you name them really, they've been here and lectured here. So these walls have heard some interesting things. And we have the very, very great pleasure tonight indeed to have my good friend, Lawrence Krauss, very distinguished physicist, a great communicator about physics, somebody who's done very important work in physics. You will know, those of you who have done your homework on Lawrence or have been avid readers of his for some time, that he was one of the theoreticians who spotted that there might be dark matter and energy in the universe. And then some folks later on went and made the observations and got the Nobel Prize for it, but they wouldn't have got it if it hadn't been for Lawrence. And Lawrence is still active, still working, still busy in physics itself, but also busy as an activist. At the moment, he's trying to bring down Donald Trump before Donald Trump gets up. But he is an indefatigable communicator about this very, very great adventure, the greatest adventure, really, of humankind, which is the natural sciences, our understanding of the structure and properties of the material universe. And here's somebody who knows something about it, and he's going to tell us something about it right now. And by the way, this introduces Lawrence's very latest book, not yet out on the shelves, but it soon will be, and he'll tell you about it in a minute. Lawrence Krauss.
Thank you.
Thank you.
Thanks. It is a pleasure to be back here, and it's an honor to be doing this lecture. It indeed has had a distinguished history. As I was telling Anthony, they ran out of the distinguished people, and now they had to go for a physicist like me. But I put this up. I'll come back to it. But the title of the story, which is the title of my new book, is the greatest story ever told so far. And so I thought I'd begin as a good storyteller might, in fact, a good British storyteller. So I figured it's the best of times, and by that I mean that the Large Hadron Collider is operating and has not created a black hole that would destroy the world, but it is indeed also the worst of times. Well, let's get rid of him, but okay. And what is, I put this up because, you know, one of the things that physics lectures do take us away from the myopic crap that we have to deal with. But also what I want to talk about is really the greatest intellectual adventure that humans have ever taken, and in some sense the greatest aspects of being a human. So this is the worst aspects of being a human, and it's so nice that we can periodically rise above that the awful experiences I'm having right now, and we are, and you will. Anyway, so let's go now back to the picture I started with, which is Van Gogh's Starry Night, which is one of my favorite images of his. When I look at this, I wonder what he was thinking when he painted it, because did he really see this image? Picasso was famously said that he painted what he saw, and obviously lied. But you know, Van Gogh was kind of unstable, and so the question is this what he saw, or is this the hidden reality that he saw was underneath? When he looked at the sky, this is what he felt was underneath. It's that hidden reality, which is the title of this lecture, that is interesting to me, because we're hardwired to want there to be more to the universe than we can see. And science has certainly provided fodder for that. The science has discovered a world that many aspects of the world we can't see, some of which I'll talk about. It's also been responsible for religion But it's this notion that there really is that there's a tip of a cosmic iceberg that we're somehow seeing. And the question I have is, what if this is what he really saw? Okay? What if the world was an illusion? What if the world we really see now is an illusion? And that's the subject I want to talk about, because it really is. The world we see is an illusion. And a better example of that is this image, which I'll come back to, which is icicles on a window, which you may, again, get cold enough someday here to have, although not if Donald Trump has anything to do with it. But so they're beautiful, and it's interesting to look at this pattern on a window. But when you do, you notice that the crystals are in all different directions. There's nothing particularly special about them. But ask yourself, what if you lived on one of these ice crystals? What if you lived on this one right here? What if you're a physicist living on this ice crystal? What would the world seem like to you? Well, it would be obvious, first of all, there's one direction that's very special. That direction there. And the laws of nature would be very different in that direction than they would be perpendicular to that line. And so the science, certainly the experience you'd have, is that it was natural, ingrained, that a very central property of your existence was the fact that this direction was special. And religions would be based on that somehow that direction was ordained by God and designed so that you could live in the world in which you're living. And the point is, this is an illusion. And it's an illusion we can see because we're outside of that system. Wouldn't it be amazing if scientists on that crystal could somehow divine that the real world was quite different than the world they see? And that's the story I want to tell you about, the revolution that's really taken place over the last century in our fundamental understanding of the universe, of matter and energy on its smallest scales, that has revealed this illusion that we have, but also revealed that things that we hold dear, including our very existence, are an accident. That the illusion of design, among other things, as you'll see, is an accident. So that's where I want to go, and that's a story I want to tell, and I do think it's the greatest intellectual journey that humans have ever taken. And it saddens me that it's not more well understood, and I'm very happy to have written the last book about it, because many people think of the 20th century revolutions that have taken place, Einstein and quantum mechanics, but there's actually a period much more recently where, in fact, I think in the far future, when people look back, they'll say the most revolutionary period of the 20th century was not 1905, was not in the 1920s, but actually was much later. But that isn't well known, and I want to relate it to you now. Okay. This is our universe, as seen in a rather grainy image right now. But this is the deep Hubble Deep Field image, and we already know that a lot of my last book, in some sense, was about the fact that this image, in some sense, on the larger scales, is sort of an illusion. That the important stuff is not the stuff we see, but the stuff we can't see, and that really dominates the universe. And in fact, I've lectured in this very hall, about that subject. But I want to go back to say, well, when we look at this universe, it inspires us to think about what caused all this. And I go back, and it's not just because my friend Anthony Grayling introduced me that I want to begin with philosophy. But as many of you know, I'm a great lover of philosophy. And I begin with this fellow. And whenever I ask who this is, and I'm not going to do this because I don't want to embarrass you. Everyone always says Aristotle, and it isn't. Okay, it's Plato. And for me, Plato was profoundly important because I was forced to read him when I was in high school. I grew up in Canada, where they educate you, and so I read Plato's Republic, and there was a part of the Republic which has stayed with me ever since, the allegory of the cave, and so I went back to my high school book and I found a drawing from it, which is this. So Plato argued that we are, in fact, reality is not what we see. what we see is a shadow of reality. And he used this example of a cave. He likened humans to being individuals in a cave, chained to a cave, so they could only see the walls of the cave. And outside was here, and the light from outside came back, and also there was a fire behind them, and they could see people on this roadway, but they could only see the shadows. So their world was just a shadow of reality. And he said, well, you know, the job of the philosopher, mathematician, is to discern, based on those shadows, what reality really is. The job of modern physicists, say. And he said that if you that you could try and do that, but if you were ever dragged out to the sunlight, not only would it be incredibly painful and disturbing to see the true nature of reality, but if you ever did settle down and see it, if you ever came back and tried to relate to the people back in the cave what you'd seen, they'd think you were crazy. And as a physicist, I'm familiar with that feeling, because the esoteric nature of particle physics is so far removed from human experience that many people just give up, but also say it just, you know, what's the point, or it doesn't make sense. And so, but the other image, by the way, which is interesting, this is dated. It dates me because this book is from the late 1950s, and so you notice that the people that are bound here on the wall, these scantily clad women in bikinis, which I think is although I understand actually. Donald Trump's labor secretary uses that now in his ads as well, but it is historically wrong, because in Plato's time it would have been young boys. But in any case, those individuals would have seen a reality that's different than the reality we're privileged to know about because we live outside the cave. But we can imagine some of the misrepresentations about reality they may have had, and one of them is this: there'd be no idea of length. We know what length is. Things have fixed length, and we're familiar with that here. But in the cave, length would have no meaning to them, because they might see the shadow of a plastic ruler, say, that behind them, where the light could go through them. And sometimes the day would look like that, and sometimes the day would look like that. And they'd say, well, clearly objects change their length randomly. And then, if there was a sufficiently intuitive and thoughtful philosopher, that person might say, you know what? Actually, we're seeing the shadows of reality. And what we're really seeing is a two-dimensional projection of a three-dimensional universe. And so, just as, let's see, oh yeah, okay. So you know, if my arm is this long here, but you see if I rotate my arm, it gets shorter. And if you couldn't see that, I'll just show you with this here. So if we look from above here, if I have a ruler that's parallel to the wall, the shadow of the ruler is that long, but of course if I rotate the ruler in this extra dimension, then the projection of the shadow on the wall becomes smaller. So if the philosopher, mathematician, scientist eventually was smart enough to realize this, they'd say, really there is such a concept of length. But the real world is three-dimensional, and we're only seeing a two-dimensional projection. And so length has physical meaning. So that would have been interesting, and that gives you an example of the kind of things that you have to think about that go beyond your experience. And we'll come back to this in a bit, because I want to jump ahead to this guy here, and you're a British audience, so you may know who this is. Who is it? Michael Faraday, that's right. The greatest experimentalist of the 19th century. An amazing individual in many, many ways, in fact, but not least because he achieved his eminence without any formal education. He was a bookbinder's apprentice, and as I was just telling the students at Anthony's College, there's a valuable lesson to be learned from Michael Faraday if you're a student, which is to suck up to your professors. He attended the lectures of Humphrey Davy, who was head of the Royal Institution, not far from here, and he attended those lectures, and he took beautiful notes, and then bound them in a book, which he then presented to Humphrey Davy. He said, "Can I be your assistant?" And of course, he became his assistant, and eventually rose to become the head of the Royal Institution. And in fact, I think he may have even established the Christmas lectures. I'm not sure, which he gave for many years. But Faraday, because he wasn't trained as had no formal education, wasn't comfortable with mathematics. in general. In fact, he said he only wrote down one equation in his life. But of course, he discovered the laws on which everything in this room is based. Ultimately, the laws of electricity and magnetism that govern our lives. And he did it with a laboratory with lots of esoterica, which this is a story I like to relate to politicians because it didn't seem very practical at the time. And there's at least an apocryphal story, or two or three, I've heard different versions of it, about someone like Gladstone coming into his laboratory and looking around and seeing these frogs jumping and all these other things happening, wheels, and said, what use is any of this? And there's two answers that two different answers I've heard that Faraday is supposed to have given. One was, of what use is a newborn baby? Okay, well, that's okay. But the better one, he said, is, what are you talking about? This is so useful that one day you will tax us for this. And he was absolutely right, because he established the laws of the electric power is based on, and we get taxed on it now. Now, he had problems with math, as I say, and he therefore used crutches, mental crutches, to try and understand pictorially what was happening, say, with the simple repulsion of two electric charges. And in a sense, he answered a question that Newton himself had left aside. Newton discovered the laws of gravity, of course, but never answered the question, how does the Earth know where the sun is to fall towards it? And he said famously, hypothesis non fingo, and I frame no hypothesis. He just figured out how gravity worked, but didn't worry about why the Earth knew the sun was there. And in fact, so there's the same problem with two electric charges. How does one electric charge know the other electric charge is there? And Faraday resolved this in a way with his mental crutch. He pictured an electric charge as having these lines going outside of it, and the number of lines would be proportional to the magnitude of the electric charge. He called that the electric field. And then he could understand what happened. He said, if I put another charge down somewhere in space, it doesn't know that charge is there. It feels the field lines coming from that charge. So if I put another positive charge here, it'll be repelled in the direction of the field lines. And it gets even better, because if I put two charges together, they both have field lines, and the field lines repel, so I can sort of imagine how you draw them. And the interesting thing is, these are exactly right. They reproduce the mathematics, the algebra of the electric field perfectly. So they're an exact math representation. His crutch gave him all the right answers. So for example, if you put a positive charge right there, it's going to zing off in that direction. And in fact, there's twice as many field lines there as there in that. So the force would be twice as big as that one. And it all works out beautifully. So that was just a mental crutch for him, these electric fields. So hold that thought for a second. The other thing he discovered was, and that's the reason we really remember him, was that up to that point it was well known that there was some relationship between electricity and magnetism. That if you moved a charge and had an electric current, you'd create a magnet. That was well known. The French had shown that. And so fine. And so people said, well, if a magnet can create an electric force, if an electric force can create a magnet, okay, I make a charge move along, and it makes a magnet, and then I can attract another magnet. So moving charge can create a magnetic field. Can a magnet affect a charge? It should be reciprocal in some way. And people had tried for the longest time and couldn't. And they brought very strong magnets near charges, and they couldn't get anything happening. And Faraday, by accident, of course, discovered the relationship. He had two current loops, one connected to a battery, and the other one not, but a current loop. And when he connected to the battery, so a current began to flow here, and it became a magnet. Suddenly a charge flowed in that other loop. What he discovered was that a changing magnetic field, because as that becomes a magnet, it starts out at zero and becomes stronger, a changing magnetic field could produce an electric force in that particle. So indeed, there was a reciprocal relationship. In some sense, a moving charge could produce a magnetic field, and a changing magnetic field could produce a force on a charge. And ultimately, that created an important step, which in fact the next person I want to show you finished. This is the most famous theoretical physicist of the 19th century, and the greatest. And who's this? Maxwell. I love the fact that we're a literate audience. It's great. Okay, James Clerk Maxwell, who was an amazing guy, Scott, and there's an interesting history. He died very young, but he still he's younger than many of the people in this room, but he did an incredible amount in that time. And he was a mathematician as well. He was mathematically literate. And so what he did was he realized that in order to make the discoveries that Faraday had made, to make it all consistent, you had to fix things up, and he made what we now call Maxwell's equations, the 4 Maxwell's equations that undergraduate physics students have on their chest, and with the 4 equations, and let there be light, because not God, but Maxwell demonstrated how there would be light. Because what Maxwell discovered, and it is indeed, in my opinion, the most exciting calculation you can do as an undergraduate physicist, I think, is he realized the following. If I take a charge and shake it, okay, then what's happening? Well, I'm having a current first I have a current, so I'm producing a magnetic field here, but the current is changing. So the magnetic field I'm producing here is changing. But if I have a changing magnetic field, this changing magnetic field is going to produce an electric field here, which is changing. But that changing electric field here is going to produce a magnetic field there is changing, which is going to produce an electric field here, and changing all the way. And you're going to get a disturbance that travels out. And the amazing thing is, by measuring the strength of the force between 2 electric charges in the laboratory, and then by measuring the force between 2 magnets in the laboratory, measuring those 2 fundamental constants of nature, he could calculate what the speed of that disturbance would be, and lo and behold, when you do that calculation, you discover it's the speed of light that was measured to the speed of light. Thereby answering the question, what was light, which had been around since before Newton, and discovering that light was a wave of electric and magnetic fields. And that was amazing, because electric and magnetic fields were an intellectual crutch that Faraday had developed in his mind because he couldn't do the math. But they weren't just an invention of the human imagination. They were as real as the hand in front of your face, because you wouldn't see the hand in front of your face. It's the electric fields. It's light itself. So this imaginary thing that Faraday had developed turned out to be essential. But it also meant that they completed the most amazing unification, the first amazing unification in physics. 2 things which seemed very different, an electric field and a magnetic field, were seen to be really different aspects of exactly the same thing. One person's electric field would be another person's magnetic field. It just depended upon what you were doing. If you're standing next to an electric charge and you're a charge, you feel an electric force. But if you're running compared to that electric charge, that charge is moving with respect to you, and you feel a magnetic force. So really, they were different facets of the same thing. And that is the hallmark of progress in science, when disparate parts of our universe are seen to be reflections of the same thing. Just like for Plato's people, that in fact different length objects were really seen to be different reflections of the same thing. That's the hallmark of progress, and that's what you generally look for and understand as being real development. So that beautiful development of Maxwell's completed the great unification, the first great unification of physics. That was in the 19th century. And then we now move to the 20th century. Oh, I just have a picture of the electromagnetic field, but let's skip that because there it is. But we will skip it eventually when this thing starts. There we go. This guy, well, you all know who that is. I don't have to ask. Okay, you've all heard of him. But it's interesting. He is a paradigm for people, and he affects many of us in many ways. In my case, every day I get about 5 emails from people who tell me the following. Everyone says I'm crazy, they say. But everyone said Einstein was crazy. Therefore, and then they say, and now this is the real kicker, because this is when I know to press delete. They say everything you think you know is wrong. All of modern physics is wrong. And just like Einstein, I can show you that it's all wrong, because that's what Einstein did. He showed it's all wrong. But what they demonstrate is a profound misunderstanding of science. Scientific revolutions do not do away with what went before them. In fact, what survives the test of experiment will always survive the test of experiment. It will always be, in some sense, true. Newton's laws, simple laws of motion, have been supplanted at scales, small scales by quantum mechanics and large scales by general relativity, but they're absolutely true for the motion of baseballs and cannonballs and cricket balls, to the extent that anyone cares about that. And so what Einstein actually, the brilliance of Einstein was quite the opposite. What Einstein realized is that there were two aspects of reality that had survived the test of experiment that were inconsistent with each other. But he said, well, what was he going to do? He didn't throw them out. What he did was find a way to make them consistent. So what are they? Well, one I've already prepared your minds. That's Maxwell. Maxwell said, if I shake a charge, an electromagnetic wave will go out, and the speed of that wave will be determined by measuring the strength of electricity, the strength of the force of two electric charges in the laboratory, and the strength of magnetism. Okay? So that's there. Now, the other one that was tested by hundreds of years of observation was Galileo. Galileo's great discovery was that Aristotle was wrong yet again. Anthony and I have had this debate because I'm profoundly influenced by the fact that it seems to me Aristotle was almost never right. Well, when he talked about the physical world. But Aristotle did what human experience tells us, with common sense, which is that all objects like to go to rest. You move them and they stop. So being at rest is of special significance. But what Galileo realized is that's just an accident of our circumstances, because he gave these examples of if you have a ball or you slide on ice, you don't go to rest very much. If I have a ball on a very smooth platform, it'll go for a long way. So things don't naturally go to rest. You can imagine, in fact, that if you get rid of this extraneous thing called friction, that the objects will go on forever. And what he said, which laid the basis for Newton, is that the natural state of motion is to not change its state of motion. Being at rest, you stay at rest. But there's nothing different from being at rest than moving at a constant speed. In fact, the way we frame what he said now is that there's no experiment you can do that will tell you if you're moving at a constant speed or at rest. You all had the experience of being on a subway train here in London and in the station, and for a moment the train on the other side starts moving, and you don't know if you're moving or they're moving. And the answer is you can't do any experiment until you start shaking and you're not moving in a constant speed. Or when you're in an airplane, if the windows are closed and you throw a baseball up or a coin, it comes back down. There's no way you can prove you're moving. Okay, it's just like if you're standing still, like you're doing here, right? Wrong. Okay, we're moving around the sun at 30 kilometers per second right now. 30 kilometers per second. The sun's moving around the galaxy at 200 kilometers per second. But we keep saying we're at rest. That's because it feels like we're at rest. That's because there's no way to tell the difference if we're moving at a constant speed. Okay, those are the two things. There's no experiment that'll tell you whether you're moving or standing still. That's Galileo. Maxwell, shake a charge, moves out at the speed of light, determined by those two fundamental constants in nature. Now, the average person might not see those as being problematic, but Einstein realized they were completely inconsistent. And I can explain this to you. The example that I'm going to present, I first thought of when my daughter was very young. So I will use projectile vomit as the. So let's say I used to drive her in the car when she was young to nursery school, and she didn't like the car very much. And so let's say we're driving along at some slow speed in traffic, say 20 miles an hour, and so someone watches me. I'm traveling 20 miles an hour, and someone on the ground sees the car go by 20 miles an hour, and she's in the back seat, and she projectile vomits and hits the back of my head from the back seat to the front seat, and it goes at 10 miles an hour in the car. So the vomit hits me at 10 miles an hour. But of course, someone on the ground watching that, laughing, sees the car moving at 20 miles an hour and the vomit at 10 miles an hour in the car. Therefore, the vomit is moving with respect to them at 30 miles an hour. What a great audience. Okay, great. Good. No problem. But now let's say my daughter is a 21st century kid, and she's a little laser that she plays with. And so she shoots a laser beam at the back of my head. Okay? Laser beam travels at the speed of light. What does this person on the ground see when laser beam? Well, the car is moving along at 20 miles an hour. The laser is in the car, and the laser is in the car moving at the speed of light. So the person on the ground sees the light ray as traveling at the speed of light plus 20 miles per hour. That makes sense. Okay? The problem is that's inconsistent with Maxwell in a way, because Maxwell says when I shake an electric charge like I do in this laser, a light ray goes out and it travels at the speed of light, and that's determined by the fundamental strength of electricity and the fundamental strength of magnetism. But that's inconsistent with Galileo, because if the person on the ground sees the light ray as being the speed of light plus 20 miles per hour, that must mean in their laboratory the strength of electricity and the strength of magnetism is different. Because Maxwell tells me that the speed of the light ray is determined by the strength of electricity and the strength of magnetism. Therefore, if this person on the ground sees it at a different speed than the person in the car, that person on the ground must make a different measurement in their laboratory for the strength of two fundamental forces. But Galileo says that's not possible because there's no experiment you can do that will tell you the difference of whether you're moving or standing still. So they both can't be right. It doesn't work. And the brilliance of Einstein was to realize, well, they're both right, because they both, for hundreds of years of Galileo and less than 50 years for Maxwell, those things survived the test of experiment. They can't be wrong. I can't throw them out. So what he figured was a very creative way to make Galileo and Maxwell consistent. And that way was to say, well, what is speed? Speed is distance traveled in some time. So if two different observers moving with respect to another are going to measure light to have exactly the same speed with respect to each of them, which is crazy, that can only be possible if measurements of distance and measurements of time are different for each of them. If the measurement of distance and your measurement of time is relative, depending upon your relative state of motion. And that was the brilliance of Einstein, that realized that would bring the two together. And then, of course, there were implications of that, and there are three of them that I can talk about here. One of them is that, indeed, if I'm moving in a car with respect to you with this pointer, the length of the pointer, which may be 8 centimeters or something like that, for you, that object will be, if I'm moving fast enough, say 4 centimeters. And people think this is sort of some illusion. You think it's 4 centimeters, but it's really 8 centimeters. But it isn't really 8 centimeters. For me, it's really 8 centimeters. But for you, it is really 4 centimeters. It is both. Because there's no experiment you can perform that'll tell you it isn't 4 centimeters. And therefore, if you think about it, and this is really important for Einstein, what we think of as reality is operational. It's what we measure. And if every measurement we make is consistent with something, that's what it is. There's no independent meaning of length except what we measure. So, it's 4 centimeters for you, it's 8 centimeters for me. It's even worse, because your ruler, which you hold up, will be 8 centimeters for you, and it'll be 4 centimeters for me. It's reciprocal. But it's true. And both people are true, are correct. The other thing is that simultaneity changes, that two events that happen at the same time for me in different locations will happen at different times for you, which is one event will happen before the other for you, even though they happen at the same time for me. And again, we're both right. And that may cause problems for some of you with cause and effect, but I'm not going to deal with here. You can ask for that in the question period. It turns out it's no problem. The last one is the one that science fiction writers use so much, and that is that my clock ticks more slowly than yours if I'm moving with respect to you. And we measure it every day in undergraduate physics laboratories. It really is true. Clocks slow down. It's not some bit of science fiction. It's really true. Now, these three implications actually laid the basis for the second great unification, which wasn't really due to Einstein, but due to his math professor. Okay? And I prepared your minds for it. If you look here, this looks very similar. In fact, it's exactly the same as the picture I showed you in Plato's cave. Einstein's math professor, Hermann Minkowski, one of the few people who Einstein admired, although he didn't go to his classes, in 3 years after special relativity was developed, said, henceforth space by time by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What did he mean by that? Well, he realized that what Einstein had done, in fact, was not a theory of relativity, but a theory of absolutes. That what Einstein had done was unify space and time in a way that Einstein didn't even appreciate. And the reason for this is that light travels so fast that we think things happen instantaneously that don't. I take a picture of this room, if I could just see that damn light wasn't in my eye. And I take a picture of this room. I took a picture now, right? No, it's not now. It's then. Because for the people in the back of the room, because the light took some time to get to me. So the people in the back of the room, the image of the people in the back of the room is a billionth of a second before the image of the people in the front of the room. So I'm taking an image that's spread out in space and time. It's spread out in space, but it's also spread out in time. So we all are looking at three-dimensional slices of space and time. And what Hermann Minkowski realized is that the mathematics of Einstein, that Einstein's relativity developed, in fact, tell us that when I'm running with respect to you, I'm kind of like seeing a different slice, a rotated slice, in a four-dimensional space of three dimensions of space and time. And so the effect in that four-dimensional space is the reason lengths look different. Remember, when I rotate my ruler, the length gets smaller in the projected direction, this direction. But if this is the time direction, then, well, if it kind of rotates, then in one person's frame, the time at either end of the ruler is the same, but the other end, for the other frame, the time at one end of the ruler is different than the time at the beginning of the ruler, which is what happens. So the mathematics is a little more complicated than a rotation, but effectively what Minkowski realized is that we live in a four-dimensional space-time. And what we see at any instant, depending upon our relative state of motion, is a different three-dimensional slice. We're just like the people in Plato's cave who saw a two-dimensional space and didn't realize it was part of a three-dimensional world. But we live in a four-dimensional space, and we now call it Minkowski space in honor of Hermann Minkowski. The second great unification caused simply by the unification of electricity and magnetism. Space and time became unified. Okay. Next, we jump ahead. Who's this? Feynman, of course. It's on my book over there, so if you bought it, you see the picture. It just occurred to me. Okay. What Feynman realized, and actually before him, Paul Dirac, but Feynman sort of explained it in a way that people could, and Dirac couldn't talk to people, but is that when you unify, the next great development, of course, was quantum mechanics. It happened after relativity. And quantum mechanics says that at very small scales, strange things happen. Very strange things. The world becomes really quite unintelligible in terms of common sense. Electrons can be doing many things at the same time, and perhaps the most important aspect of this was that what became called the Heisenberg uncertainty principle, which is that there are certain quantities that I can never measure exactly in nature, a certain combination of quantities. It's not a property of my measuring device, but rather a property of nature. I can know if I have a little small particle, I can know where it is at any given time with it's precisely as I can measure it, but then there's an uncertainty in knowing which direction and how fast it's going. Or I can know which direction and how fast it's going precisely, but then I won't know exactly where it is. The net effect of Heisenberg uncertainty principle is I'd like to say that the laws of physics on small scales are the same as corporate America or in Washington, and actually in this administration they're exactly the same. But in the upcoming one. Because basically the law is if you can't see it, doesn't matter. Anything goes. Okay? And so that means that things can happen on microscopic scales that violate what you would measure, otherwise called the laws of physics, but as long as you can't measure them, it's okay. In quantum mechanics, they're happening all the time. And that means that, and it was Feynman who first realized that this implied something interesting. It really implies that empty space is a boiling, bubbling brew of virtual particles popping in and out of existence all the time. I mean, particles can't pop in and out of existence in a classical world because they violate energy. You create mass where there wasn't any mass. But you see, as long as they disappear very quickly, Heisenberg says it's fine. And that's happening. And in fact, this is actually an actual calculation of the space inside of a proton. This was shown at the Nobel Prize ceremonies. I was there, actually, and it was the people who allowed that calculation to be performed. And most of the properties of the proton are determined not by the fact, as we teach high school kids, that there are 3 quarks in a proton. That's irrelevant. Most of the mass of the proton comes from these virtual particles. So you can't see them directly, but they have an incredible impact. But this also allowed Feynman to reframe the beautiful laws of electromagnetism that Maxwell had developed, and to think of the electric force as being slightly different. That when 2 electrons repel each other, what's really happening is one electron is emitting a virtual particle, the quanta of the electromagnetic field we call a photon, which comes in particles. And it's virtual. It takes away a little energy, potentially, and therefore it can't exist for a long time or violate laws of physics, but it turns out the amount by which you can violate energy is proportional to the time, inversely proportional to the time in which you measure it. So if it doesn't exist very long, then there can be some small violation of energy. In any case, it gets absorbed by another electron before you could ever measure it, and that causes that electron to be repelled. So the electric force is thought of as the exchange of particles. And we now think in the modern world, all forces, because of quantum mechanics, are due to the exchange of particles. Now this theory, based on the exchange of virtual particles, is the best theory in nature. Quantum electrodynamics, as it has become called, and Feynman and others won the Nobel Prize for it, can predict observations that can be compared with those observations and get agreement to 14 decimal places. There's nowhere else anywhere else in science where, based on fundamental principles, you can make a prediction and compare with observation to 14 decimal places. So this is really, and it only works because these virtual particles. Okay, great. That works great. Now, this is the quantum understanding of the electromagnetic field, and Einstein got hung up for a long time in his life trying to unify gravity and electromagnetism, and that's because he got out of touch with physics. He also didn't buy quantum mechanics, so he's really out of touch with physics, and that's why he didn't make any progress for that later part of his life. And the real reason he got out of touch with physics is that it turns out that that electricity and magnetism are not, and gravity are not the only forces in nature. So why bother just trying to unify them? Because we discovered there's another force in nature, and that force produces something that's amazing. When I was in high school, I first learned, and it amazed me, and I hope it'll amaze some of you if you don't know this, that the neutron is radioactive. This should surprise you because you're made up of neutrons. Most of the particles in your body are neutrons, more than protons. Now, a neutron, if I put it here in space, will decay in 10 minutes by radioactivity. You will notice, some of you somewhat painfully, that you've been in this lecture longer than 10 minutes. And you're still around. So what gives? It's a remarkable accident. So the person who first described this decay theoretically was another one of my heroes, Enrico Fermi, who was the last great particle physicist, basically, or nuclear physicist, who was equally adept at theory and experiment. And he developed a theory of describing this decay of a neutron, and then also did experiments. He won the Nobel Prize for his experiments. And he also, of course, worked on the Manhattan Project and created the first nuclear reactor underneath the football field in Chicago. And as I like to say, they did it under the football field at the University of Chicago because if anything happened, you just kill football players, there'd be no loss. But the neutron decays into a bunch of particles. It decays into a proton, and although this time it's called a beta particle, it's really an electron, a proton, electron, and another neat particle, my favorite particle in nature, called a neutrino. Okay, that's the decay of a neutron. It decays in 10 minutes. Why doesn't it decay in your body? Well, it turns out the mass of the neutron is just slightly greater than the sum of the mass of a proton and electron, and a neutrino is almost massless, okay? So if it can only decay into a proton electron because it's more massive. If it was less massive, it couldn't decay because it would violate energy for a less massive object to decay into 2 more massive objects. But what happens when I put a neutron in a nucleus, like helium or oxygen or nitrogen or carbon. It gets bound in the nucleus. What does it mean to be bound in the nucleus? Well, to be bound, it means it takes energy to get it out. It loses energy when it falls into the nucleus. But Einstein told us that E equals mc squared. Therefore, when it loses energy and falls in the nucleus, it gets lighter. And when it falls in the nucleus, it's too light to decay into a proton and an electron. So you're only around because happily nuclei formed in the early universe and in stars that made up atoms in your body. And so it's an amazing fact that it's just the fact that the difference in mass between a neutron and a proton and electron is less than 0.1% of the mass of the neutron. And therefore, when you drop it into a nucleus, it's stable. But, I mean, that really has nothing to do with what I'm going to talk about later, but I thought it's a neat little fact that you should know. But the fact that a neutron decays means something happens. There's a new force in nature. The fact that it takes so long to decay meant this force was called the weak force. Because the standard time over which things happen in atoms, for example, light is emitted and electrons jump around, is more like a millionth of a second. But a neutron took 10 minutes to decay. So whatever force is responsible for that decay is very, very weak. And, of course, it only happens over the size of a nucleus. You never see this force on large scales, but in a nucleus, you see these beta particles, electrons, spitting out, and that was what was called beta decay. So it happens, some strange new force exists inside the nucleus that's very weak. So why the hell should we care about it? And the answer is we should care about it because it's responsible for our existence. It's that very force that powers the processes inside the sun that produce nuclear fusion, that produces the energy that allows all of us to be alive. And so this weak force is very important to try and understand. And people tried to understand it. And as I often say to people, physics is just like Hollywood. If it works, repeat it. Just keep doing the same thing. Halloween 16 or whatever. Anyway. And so physicists said, okay, well, we're pretty good at this repeating stuff. We know how electromagnetism works. So let's imagine this new force looks exactly the same way. This is called a Feynman diagram, by the way, after Mr. Feynman. And let's imagine that the decay of a neutron, which happens to be made of quarks, but it doesn't really matter, it eventually produces these particles, an electron, neutrino, and that happens because of the exchange of a particle, because that's what happens in forces in nature. But there's a difference. The electric force, the electromagnetic force, is long range. This happens only over the size of a nucleus. How can we understand that? Quite simple. Sort of quite simple. The photon is massless. That's a vital aspect of electromagnetism. The photon has no mass. This allows electromagnetism to be long range. Why? Because I remember when I told you that this thing can only exist for a little while because of the Heisenberg uncertainty principle. That's true, except because the photon is massless, it can carry arbitrarily small amount of energy. And that means an electron here can emit a virtual photon that travels all the way to Alpha Centauri and repels and is absorbed by an electron in Alpha Centauri, producing a very small electric repulsion. The electric force is long range. It's infinite range. It goes down as 1 over r squared, but it's infinite range. That's only because the photon, the virtual photon, can exist for a very long time because it can carry a very small amount of energy. But now you see, if I make the particle that conveys this weak force massive, then it has to be absorbed very quickly because it's got a finite mass. It always carries non-zero energy away, and therefore it has to be absorbed very quickly by the Heisenberg uncertainty principle or it will violate energy conservation. So all I have to do is to make a theory that looks exactly like this theory, but make this particle massive and everything works. Except it doesn't. Because the problem is the mathematics, the beautiful mathematics that makes this photon massless, the symmetries of electromagnetism, the beautiful Maxwell's equations, tell you in quantum mechanics that you can do wonderful calculations. When you make the particle massive and you do the same quantum mechanical calculations, you come up with infinity. And physicists don't like infinity because it's crazy. So I just want to have a slight digression because mathematicians love infinity. And I know Bertrand Russell gave a lecture here, and I'm feeling his I'm channeling him. So I want to at least give a chance for the mathematician. So I want to talk about another. David Hilbert did not give, as far as I know, a Conway lecture, but he was really the greatest mathematician of the turn of the century, the last century. And he gave an example to show you how crazy infinity is. And I want to just give it to you to show you part of the reason physicists don't like infinity, because you can do anything with infinity. The example he gave was, we call Hilbert's Hotel. Actually, he called it Hilbert's Hotel. And it was quite simple. Imagine an infinitely big hotel. Say you go to Las Vegas. And you have an infinitely big hotel that holds an infinite number of people. And I can represent this hotel simply as a number line here. And I number the rooms, 1, 2, 3, 4, 5, 6, all the way to infinity. Okay? Now, I go into the hotel and I say, can I check in? And he says, well, all the rooms are full. So you say, okay, I'll leave. And he goes, no, I can accommodate you. And you say, how? And he says, well, it's quite simple. I move the person from room number 1 into room number 2, the person from room number 2 into room number 3, and so on and so on and so on. And now room number 1's empty. No problem. Okay, well, that may not bother you so much. But let's say you have an infinitely big family, a Catholic family, and you bring them into the thing, and you say, I want me and my infinite number of children to come in. And he says, well, the room's full. The hotel's full. You go, okay, sorry. And he goes, no, I can accommodate you. How? So I move the person from room number 1 into room number 2, the person from room number 2 into room number 4, the person from room number 3 into room number 6, and then only the even numbers are occupied. And there are an infinite number of odd numbers, so it's fine. So you see, when you try and add and subtract with infinities, you get crazy things. And even crazier things, which I won't show you, which, as I was actually telling students the other day, were responsible for string theory. But the point is that mathematics, if you have infinities in physical calculations, you get results that are crazy. So you had to get rid of them. And clearly, the standard theory that made this, which should have worked, doesn't work. So how can you resolve the fact that the weak force is short range and the electric force is long range, and there would seem to be no mathematical way to understand that? And the answer is the following. Maybe the universe we experience is really an illusion. Maybe mass is an illusion in some real deep way. And to understand that, I talked to you about living on an icicle, but imagine living in a superconductor. What's a superconductor? Well, here's an icicle, so let's cool things down. And Kamerlingh Onnes in 1911 discovered if he cooled mercury down to 4 degrees or less above absolute zero, something very strange happened. This was measuring resistance. And suddenly, to his surprise, at a specific temperature, the resistance goes down as things get colder because the atoms jiggle less. But suddenly, at a certain temperature, the resistance went to 0. It didn't become very small. It went to 0. Meaning if he hooked up a battery and get a current going and then cooled the whole thing down and then removed the battery below the superconducting temperature, the current would flow forever. Never lost. It would flow forever. And he called it superconductivity, so he was very good in public relations as well. But and of course, it's the basis of many things, including our Large Hadron Collider couldn't operate without it, and we'll get there in a second. But this weird aspect of the total electric resistance going to 0, it took 50 years for this to be understood, more than 50 years almost. And it's a weird property of quantum mechanics. The property is that somehow, it turns out in certain materials, electrons which normally repel, in certain materials, because of the property of materials, they actually attract. And they bind together and they collapse into a single quantum mechanical state. Now we would call a Bose-Einstein condensate, but the name doesn't matter. And that single quantum state behaves very weirdly. There's no resistance. But that allows interesting phenomena to happen. And an undergraduate physics experiment you can do, because now we have superconductors that become superconducting at dry ice levels. And you can do this in a lab, and people do it in universities all the time. If you put a magnet above a superconductor, the magnet will float. Why is that? Well, it turns out magnetic fields can't permeate a superconductor. And so the magnetic field lines get repelled by the superconductor, essentially, and that holds up the magnet. Why can't they make go into a superconductor? Well, if you think about it, if you try and move the magnet close to a superconductor, then there's a changing magnetic field and little currents will flow in the superconductor, but they don't ever go away. So they cancel that magnetic field. They repel that magnetic field. Okay. Now, what does it mean that the magnetic field can't go into the superconductor? If you lived in the superconductor, what would it look like to you? It would look like electromagnetism is a short-range force, because the magnetic field can only permeate a little bit into the superconductor and then it dies off. We call it a penetration depth. So if you lived in a superconductor and you grew up in a superconductor and you're a physicist in a superconductor, for you, the photon would be massive, because electromagnetism is short range. So your laws of physics would be electromagnetism is short range. Now, this should prepare your minds for this now. Because maybe we're living in a superconductor, a weird kind of superconductor. And maybe what we think of as mass is just an accident of the circumstances in which we find ourselves. And so this is where Mr. Higgs comes in. If you're swimming in water, then you can swim fairly fast. If I put you swimming in molasses, you swim much slower. You feel heavier. It's like the photon in the superconductor. So maybe, what if there's a background field everywhere in nature, like that Bose-Einstein condensate in the superconductor, but a slightly different kind, one invisible that permeates all of empty space. And some particles interact with that field. And as they do, like swimming in molasses, they experience a resistance because of their interaction with that field, and they behave as if they're massive. What if that's the case? What if the particles that convey the weak force interact with that background field, but the photon doesn't, so it continues to move at the speed of light, and it's massless? Well, if that's the case, you can draw exactly the same Feynman diagrams for the weak interaction as the photon interaction, and it's because at the fundamental scale, in reality, these particles that convey the weak force are really massless. If they interact with this background field, which happens to accidentally exist here, they look to us like they're massive, and therefore the force they mediate is short range, but at a fundamental scale, they're massless. And if at a fundamental scale they're massless, the mathematics is identical to that of electromagnetism. And if the mathematics is identical to electromagnetism, the infinities go away. And more importantly, I can actually do calculations and I can compare them with observations and get exactly the right answer. And more importantly, I can then understand, in fact, that I can unify these, and in fact, they're all different aspects of the same force. Electricity and magnetism and the weak force are really fundamentally the same. They just appear differently to us because we have this accident that there's a background field that somehow distinguishes between the W and Z's, as they're called, the particles that mediate the weak force, and the photon. It's an accident of our circumstances, but in fundamental reality, it's not that way at all. And if there wasn't that accidental field that somehow came into existence in our superconductor, the world would be very different. In fact, it would be so different we wouldn't be here. Because if these didn't have mass, it turns out we can say the same thing for all particles in nature, the particles that have mass. Electrons, protons, quarks, they're also interacting with this field, and the ones that behave as if they're heavier just are interacting more strongly. The ones that are lighter are interacting less strongly. So if that field wasn't there, all the particles that make us up wouldn't have mass. If there was no mass, there'd be no people, there'd be no planets, there'd be no galaxies, there'd be no anything. Our very existence comes from that accident. Well, that's an amazing hypothesis, and in fact, it was put in firmer form by a bunch of people who went on to win the Nobel Prize for their work, putting the mathematics down dramatically. And then it turned out the very same ideas of symmetry that led to the weak and electromagnetic interaction were then applied to the strong interaction, and these guys won the Nobel Prize for the strong interaction. And this is amazing, because this all happened in the 1960s and 70s. In 1960, we understood one force in nature, electromagnetism, as a quantum force. By 1975, we understood completely, in agreement with every experiment that we could perform, and exactly 3 of the 4 forces in nature. It was the biggest revolution in our understanding of the universe, and no one's ever heard of it. But suddenly, we had done the next great unification of physics. First, electricity and magnetism, then space and time, and then unification of two of the three forces in nature. And of course, it didn't take a rocket scientist to think that maybe all the forces in nature are unified. And physicists began to think about something called grand unification, and they became more obnoxious than they were before because they thought they could explain everything. And of course, these ideas have been interesting, but they take us to a realm of the universe that we haven't been able to explore experimentally yet. So the three forces, one type of symmetry for all of them, every observation explained, hubris in the extreme, we're going to do everything, and we haven't yet. But the point is, we have gone to such a great leap because suddenly, in 15 years, our picture of reality changed completely. The universe we see is an illusion. Except all of this so far is just a story. It's not science yet. It's like religion. Because, after all, what have we posited? We've posited an invisible field everywhere that exists throughout the universe that we can't see, that is responsible for our existence. Does that sound familiar? If it isn't the Bible, it's Star Wars. Okay? So that's not good enough. That's just a story. And what's really nice is, and what makes it physics, is if it's going to be physics, we have to test it. We have to be able to probe and see if that story is right. And we have to be willing to be completely wrong. And I have to say, I was sure the picture was completely wrong. Because this invisible field just seemed too slimy to me. I was convinced that the nature would have a better way of doing this. But there's a way to try and see if it's right. Spank the vacuum. Sadomasochism. Let's go. Spank it hard. You have to. Because in modern physics, if there's a field, there's always a particle associated with that field. And so therefore, if you dump enough energy into a single point in empty space and slam empty space with that energy, you should kick out real particles if there's a field there. If there's a Higgs field, you should kick out real particles that we call Higgs particles. So, very simply, how can you spank the vacuum? You build a big machine. You build the Large Hadron Collider. The most complicated machine humans have ever built. 26 kilometers around. If you go to the airport in Geneva and fly in, you'll just see farmland, but underneath that farmland is this 26-kilometer long ring, about 100 meters underground in most places, under the Jura Mountains here. This is the French-Swiss border, and we accelerate protons at 99.999995% the speed of light in that direction. We accelerate another beam of photons at 99.999995% the speed of light in that direction. They go around thousands of times a second between France and Switzerland without passports, and they just zoom around. And every now and then we focus that energy into single points in a few places, and we build the detectors that can look for those events. And of course, this is one such event that was predicted. And on July 4th, 2012, we celebrated. Some of us didn't celebrate. I was really disappointed because nature wasn't as ingenious as I figured, because it was just so simple. Okay? We discovered 50-ish events that looked like a Higgs. They kind of walked like a Higgs and quacked like a Higgs. So it turns out since then we've discovered much more. They are Higgs. Every aspect of this particle discovered is exactly the same as we predicted. It is amazing. And that tells us that there really is this invisible field throughout all of nature that's responsible for our existence. This accident, as the universe cooled down, this field froze, just like an icicle on a window. And before I get to the implications of that, which are profound and miserable at the same time, I want to point out that I really think that this story is humanity at its best, at its very best. Over centuries, theorists were using the ideas they could do, and the most beautiful ideas you could come up with, and building this picture, this incredible house of cards. And the great thing about it is it could have all fallen apart. It wasn't just that it was an elegant and interesting story, but it could have been wrong. And it wasn't. But then the experimentalists built these machines, and I would say that they are like the Gothic cathedrals of the 21st century. The Gothic cathedrals took over a century to build by thousands of artisans from many countries, speaking many languages, there to sort of celebrate the glory of God. The Large Hadron Collider was built by 10,000 physicists and operated by 10,000 physicists from over 100 countries. It took over 20 years to build, speaking dozens of languages, different religions, building machines that are the most complicated machines. This is one of the machines where the particles collide, and this is another one. This is a small one, the compact muon solenoid. I have a better picture of it because I'm in it. Yeah, there we go. And this machine has, by the way, this detector, single detector, has more iron than is in the Eiffel Tower. And comes in two parts. Right here, there you can go down because it wasn't operating. There's another one here about 10 meters away, the other half of it. The magnetic field is so strong in these detectors that even though they're not on wheels, if the magnetic field was turned on, those 10,000-ton pieces of iron would slam together. Incredibly intense magnetic fields produced by over 5 tons of liquid helium, which cools superconducting magnets, thousands of them located among that tunnel, and the tunnel itself has to have a vacuum that's smaller than the vacuum of space, fewer particles than if you go to the International Space Station, outside of the International Space Station. And it all has to fit together with micron accuracy and incredible difficulty of measuring each second at the Large Hadron Collider. Enough data is generated to fill more than 1,000 1-terabyte hard drives every second. That's more than the information in all the world's libraries. And somehow we had to figure out ways to use computers that could sift that information to look at this signal. It is truly the most amazing effort that humans have ever made experimentally, and it was just like the Gothic cathedrals, which pushed the technology of their time. Why? Just to discover this damn particle, and maybe a little bit more. And for some people, that just seems a waste of time and effort. But it isn't. Because ultimately, we're addressing the very questions that humans have thought about and wondered about since we've come. The questions of philosophy as well as the questions of science. Why are we here? How did we get here? What's the world made of? And the amazing thing is that in that sense, and that's why the subtitle of my new book is, Why Are We Here? And the answer is, there is no reason. Namely, it's an accident. It's just an accident. Now, we aren't done. I don't want to suggest we're done. We'll get to the accident in a second. I also like art. I particularly like the Impressionist period. And what I love about Impressionist paintings is that from a distance they're great, but when you get up close they really suck. And the same is true of the universe. So this picture is beautiful, but it's nowhere near complete. Why is the Higgs field there? Why did it exist in space? Why did it exist with the energy it has or not? Why did it give the particles the mass they have? We don't have the answers to any of those questions. And the only way to figure it out, the only way to address those fundamental questions, ultimately, is to continue to look. And we think by operating the Large Hadron Collider, among other things, we may discover the reasons. We may never discover the reasons if we don't build another collider, if they don't see anything. And you can't go up to the government. I mean, in this case, you can't go over government and say anything sensible. But you can't. Can you imagine going up and say, guess what, we operated the Hadron Collider, and we didn't find anything. Let us build a new one. Okay? It's a problem. But the point that I want to get to close is our existence is a cosmic accident. The illusion of design, which has been so prevalent in confusing people about nature in so many ways, happens at our level. The universe wasn't designed so we could exist. In fact, the fundamental properties of the universe are such that we shouldn't exist. It was an accident that somehow as the universe cooled down, this Higgs field formed in just the right way so that light was massless and the weak interaction was massive. If a different kind of condensate field had formed, then maybe light would be massive and we wouldn't be here. And maybe the particles that make you up wouldn't be massive and then you wouldn't be made up. But it's even worse. Well, or better. In fact, I view this as better. Because not only is our existence an accident, it's ephemeral, potentially. Because remember, these people would have invented their religious beliefs to say that this very single direction was so special. Just like our mass is so special. Okay? and the world we see is so special, but it's an accident. If they could see around, they'd see that really there's nothing special about that. But moreover, they wouldn't know that the next morning the sun is going to rise and it's going to melt. And it's still quite possible that the Higgs field will melt. In fact, we can do some calculations and say, based on the measured mass of the Higgs, is it likely that that field's going to melt? And it turns out if it had been much lighter, it wouldn't, and much heavier, it would have. And it turns out it's right at the borderline. Right at the borderline of where eventually it might become unstable. Now, don't get worried. It's not, if it happens, even in the calculations where it happens, it won't happen not for 10 to the 10th years or 10 to the 10th to the, it'd be more like 10 to the 10th to the 10th years. Okay, so don't sell your stocks or anything. But I find this amazing because it means the world of our existence is not just an accident. It can go away like that. And if it does, we will. You'll be pleased to know with no advance warning because it'll happen at the speed of light. But that's the world that we find we live in. That's the intellectual journey we've taken. And what it does is it means that the universe is not just an illusion, but an accident, and there's no reason for our existence. It wasn't designed for our existence in any way we can see, but it may go away. And that's the beauty, because it means it's so lucky that we are here, and we've evolved brains that can think of this and have fun. And so instead of being disappointed by all this, you should enjoy your brief moment in the sun. Thank you very much. Ooh. Oh, that was a lot.
Well, thank you very much indeed, Lawrence. Thanks.
Yeah, I need some water.
Well, people are organizing their thoughts, getting their questions ready.
Dizzy.
So to ask you.
Okay.
So you were skeptical about the Higgs before it was observed. Mm-hmm. What did you think nature was going to come up with?
Well, I had a bunch of theories in mind. I was ready to publish them when they didn't find the Higgs. And in fact, I was planning to publish them just before they didn't find the Higgs, but they found it before I could publish them. Probably just as well. For some people, extra publications are a good thing, but in general, I like publications that actually correspond to reality, which doesn't happen very often, I should say. But I thought that this Higgs field was probably that the picture obviously was partly right, because all the calculations of the electroweak theory worked. But somehow this imaginary Higgs field, this fundamental field that froze, just seemed too simple. I thought really nature would find something more complicated that would effectively act like what we see as a Higgs field, but something that really was much more interesting than just this scalar field that somehow condenses. It just didn't seem like I thought that, it's really ad hoc. Shelley Glashow, the physicist, used to call the Higgs the toilet of physics, because it's where all things happen you don't like to talk about. and it just seems very ad hoc, and it still does, in a sense. We don't know why this single scalar field would work. So I was really shocked. But the other thing that came, which is people don't appreciate, and even many of my colleagues, I found this many times in my life when I've written papers after the fact. Theorists like to think about things, but you tend not to take things seriously until the experiment's actually performed. And it's true, I predicted dark matter, but dark energy, but I didn't believe it until they discovered it. But more importantly, there are many papers I've written about things that I could have written a long time before, but it was only when the experiment was performed that I said, really, this is... And so after the Higgs was discovered, I've written papers, one of which suggests there may be a relationship between the Higgs and dark energy. It's no doubt wrong. It's ugly. But it's amazing that it's even possible. And I would never have thought of that. So theorists need to be guided by experiment. And not just because it tells us how nature really works, but it often provokes our minds. And that's why things like string theory, which are incredibly inventive and creative, are probably, in my mind, not inventive or creative enough, because it's the imagination of nature is so much greater than that of human beings. And we need to look outward. And I'm giving you a long answer, but I'll give it anyway. As I've often say, and I think this is of vital importance, and some people might disagree, but nothing important about the universe is ever discovered by revelation. Every time people have revelations based on internal examinations and not thinking about the outside world at all, it's wrong, I would argue. Okay.
You mentioned there that as a result of the discoveries of the Large Hadron Collider, you're starting to think a little bit about whether they might give us some clue about dark energy and dark matter.
Well, yeah, absolutely. And I don't know, I'll tell you a joke anyway, because Richard's been on this hall telling this joke. If you've ever read Richard Dawkins' book, one of his books, which he actually talked about the Large Hadron Collider, but there was a misspell. It's called Large Hard-On Collider, which I thought was really, physicists get a hard-on about it. But anyway, many of us thought that associated with the reason the Higgs is the way it is, there's a new symmetry of nature called supersymmetry. And what's really interesting is it predicts a whole bunch of new particles. Now, why do we care about that? I mean, it's a whole bunch of new particles we haven't seen, so you could say the theory's wrong, but it turns out for every particle in nature, there's a partner called a supersymmetric particle. And so we can say we've discovered half the particles in nature, so it's half full rather than half empty. But the neat thing is, the lightest of these will remain stable and almost invisible. And it'll have exactly the properties we need for dark matter. In fact, you can calculate from these theories how much of this stuff should be left over from the early universe, and you get enough to be just the right amount of dark matter. It all looks so perfect that most of us thought the first thing the Large Hadron Collider would see would be dark matter, the particles that make up dark matter, the supersymmetric particles. The Higgs was much harder to discover. In fact, it wasn't even guaranteed to discover it. We thought we might need another machine. And we haven't discovered those other particles. Now, the energy of the Large Hadron Collider has been turned up, the intensity has been turned up, and so they're hopeful. But it is of some concern to us, because if that theory is wrong, then it means we're back at the drawing boards. While it's of some concern, it's also exciting. Because, again, I think I've said on this stage before that if you're a theorist, the best state to be in is, or two states to be in, are either wrong or confused. Because that means there's more to learn, and I'm usually wrong and confused. So we'll see. We just don't know, and it'll be. There were two nightmare scenarios of the people who built the Large Hadron Collider. One is that it would see nothing, which is what I was betting on at the time. But the other is it would just see the Higgs and nothing else, because it doesn't tell us what direction is right. And moreover, if it just sees the Higgs and nothing else, sociologically, it may mean that there won't be any motivation of governments to say, yeah, we want to find the answer, and we may not be, because the next collider certainly has to be international, multinational, and frankly, it's really relevant at the current times, because what we're seeing in the United States and in England and in other countries is this ridiculous nationalism, this ugly head of nationalism rearing its head, and whether that ends international collaborations is an open question.
Yeah. I remember asking Tejinder Verdi, who was on the CMS experiment back in 2012, I said to him, it must have been an absolutely fantastic feeling on the day you felt ready to publish. We've seen the Higgs, we've verified it, it's great. And he said, yeah, it was great. But you know what? It would have been even better if we hadn't seen it, because then there would be so much more physics to do.
Yeah, well, everything, that standard model would have been wrong in a fundamental way. And that's really much more exciting, in a sense, because the search is always more exciting than the finding, I think. And the fact that there's more to learn is what keeps us going. And in fact, that's one of the things that's important in stories like this. That's why it's called the greatest story ever told so far. Because the best part of the story is yet to be told. And people don't realize that. They think that it was all done by sort of dead white men 100 years ago. And it's not. And there's incredible things to be discovered by the young people, if there are any in this audience, and in the future. The best, 100 years from now, the best parts of the story will be the part that I haven't told yet.
Well, the audience is very dark, actually. Can we change the lights a little bit?
It would be wonderful.
Can we have the house lights up and put the spots off so we can see who's going to ask questions?
I don't know if they're filming, but it doesn't matter to me.
Okay.
Okay.
Because I can already see there's an arm up over there near the back.
Yeah, near you in the near back.
Are there microphones as well?
They're bringing them over to him.
Yeah.
Yeah, turn the audience lights up. Yes. Yeah?
Where does that...
Uh-oh, the microphone doesn't work. Okay, try it again. There we go.
Oh, it's working.
Where does that put the holographic universe, if there's such a thing?
Okay, the question was about the holographic universe. One of the interesting aspects of string theory is it suggests that the fact that we are in this four-dimensional universe that we didn't know is just the tip of a really big iceberg, in the sense that string theory requires there to be many more dimensions in general. String theory has required many different things over the years, none of which have been tested, and none of which have really, unfortunately, allowed us to make predictions. But it used to predict 26 dimensions due to an infinity problem, and then it went down to 11 dimensions, and then a little bit less. And then the interesting thing that was recognized, and this is fascinating mathematically, is that it's possible that dimensions themselves don't mean anything. That one person's 5-dimensional universe could be another person's 4-dimensional universe. And it's like a hologram. In the sense, a picture is a 2-dimensional representation of this room. Okay? But a hologram is a 3-dimensional representation of the room. Namely, if I have a hologram picture of this room and I move over there, I can see some of you behind the person in front. That's what's neat about a hologram. It stores all the information of a 3-dimensional image in a 2-dimensional object. So in some sense, a hologram is a 2-dimensional representation that contains all the information of a 3-dimensional object. And some people have argued that it's possible that we're living in a hologram of sorts, that we're a sort of 4-dimensional projection of an underlying 5 or 6 or 7-dimensional universe. It's very interesting mathematics. There's no evidence that it's true. It does allow for some interesting mathematical connections to be made, which have been useful, but useful in describing other physical systems than the whole universe. So it's a fascinating idea, and it's part of the never-ending realization that what was called string theory was not understood at all. In fact, strings may not even be important, and that it's really a whole new developing area of mathematics that may one day pay off. But right now, we have no idea what even the fundamental objects or the physics associated with these things are. And as I say, one of the surprising realizations is that maybe even this, what we mean by dimensions, is an illusion, that we are living in a hologram. It's a very sexy idea, and that's why it's got a lot of play. But right now, there's no evidence of it whatsoever in the real world. I mean, as I say, there are small physical systems where you can mathematically solve them by solving them in another series of dimensions. So the mathematics that's been developed has been very useful in different areas of physics. But for describing fundamental reality, it's not yet ready for prime time.
Anybody else? You've got a question in the front here?
Yeah.
Have the mic.
Mike
Down
in
this
the
way.
front.
Right in the front row.
We were told years ago that the speed of light was as fastest speed
There is.
is, which seems to be quite wrong now, of course, because if you have two objects travelling towards one another at, let's say, 3/4 of the speed of light, their closing speed is obviously going to be...
You'd think so, wouldn't you?
Yeah. And
But it's not the way it works.
well, I'd like
No,
to...
that's what, no, the mathematics, special relativity is full of these catch-22s, where if two objects can be traveling towards each other at 99% the speed of light, and each of them will see each other, and the light is traveling, everything traveling less than the speed of light. But I want to be on your side here for a second, especially before you start arguing with me. That is that we lied to you when we told you things can't travel faster than the speed of light. You have to be like a lawyer and parse it a little more carefully. Nothing can travel through space faster than light. But it turns out space can do whatever the hell it wants. And in fact, in our universe now, there are objects receding from us faster than light. They're not moving. In fact, they're at rest just like we are. We're at rest in our local surroundings. They're at rest in their local surroundings. But the space between us is expanding faster than light. So they're receding faster than light, and in fact, we'll never see them. So locally, they're standing still. That's what's great about general relativity. You can be moving at the speed of light and be standing still at the same time. And that's confusing, right?
Well, yeah, I still don't understand that the collision wouldn't occur at...
Well, I mean, it's the mathematics of... The point is that each
Collision
person's...
would occur at
It's
1.5
a conspiracy of measuring space and time. The conspiracy is such that each person measures the speed of the other object because of their separately distorted versions of space and time. So they see things coming at them at less than speed c. Another example of that is one that I didn't mention, but I said I made allude to, and I think it's even more paradoxical. Remember, I told you, for observers, some people will find some things happen before the others. One observer will find this event happens before that event, and the other observer will say that event happened before that event. What about cause and effect, the kind of things that philosophers worry about? If one event, the only way you can be the cause of an effect is if you happen before it. So if it switches, then there goes out cause and effect, except for this catch-22 of special relativity. It turns out that the time difference between before and after that happened for different distant objects is always less than the time it takes light to travel between them. And since no information can travel faster than light, one object can never be the cause of the other object. And so it all works out. It's just this cosmic conspiracy that nature has to end up being sensible, but at the same time illogical. And that's really important. I'm trying to think of lessons that can be learned beyond your own confusion. And that is, and it's nothing wrong, it is very confusing. And that is that common sense is not a guide to the universe. And that's really an important thing. We've learned that, common sense is something we evolved with. And we evolved with it because it was useful to us at human scales. And Richard has said, it's useful because we learned how to run away from lions on the savannah, not to understand quantum mechanics. And so common sense is a good guide for certain things, but we shouldn't use it when we explore the unknown. Same with anthropology, same for civilization, same for many things, same for different groups. For some people, it's common sense to be attracted to a person of an opposite sex, but it's not universal. Get over it. Okay, anyway.
Look, the questioner is wearing an England rugby jersey, so the hope that something can travel faster than the speed of light is obviously wishful thinking on your part.
No, in fact, let me tell you something. There was a while an experiment discovered, you may have heard this, at the Large Hadron Collider. It looked like there was a beam that went to Italy, and it appeared to arrive faster than light, and there were headlines around the world. I immediately said it was wrong for a few reasons. One, theoretically, it was crazy, but more importantly, so it arrived something like 100 milliseconds faster than the speed of light in Italy. And I pointed out that nothing ever arrives early in Italy.
Question over there?
Yeah. Hello, Professor Krauss.
Yes, hi.
Hi. That was a really great talk, and
Thank you.
day I'm going to understand it.
The great thing is, there's a book you can get. Anyway, sorry, go on.
All right. Now, the thing that keeps me up at night is, perhaps you can comment on it, is apparently there are now 2 trillion universes in the galaxy.
2 trillion galaxies in our universe.
Sorry, 2 trillion galaxies in the universe, yes. So it's kind of gone up a hell of a lot from probably 400 billion before.
Yeah, what was in my book. Now I'm going to tell you something really neat, which isn't in the newspapers. There are 2 trillion and 400 billion at the same time. Not at the same time, but now I know, so you thought it was going to be easy. Okay, but here is really neat. This is a clear example of the fact that when we look out at the universe, we're seeing a slice in space and time. So the statement is, there are 2 trillion galaxies in the observable universe. And that's true. Because what's happened is astronomers have been able to look at far greater distances to see fainter galaxies, and they measure a lot of small galaxies, a lot more small galaxies, small faint galaxies than we thought existed. But what happened? Those small faint galaxies combined together, collided together over time to form the galaxies that exist today. Our Milky Way galaxy is still cannibalizing other small galaxies. So if you look out at the universe, you see 2 trillion galaxies. But that's because you're looking back in time. If you asked how many galaxies exist today, it's more like 400 billion. Because all those galaxies, many of those galaxies combine together to form galaxies. But when we look out at the universe, we're not seeing it at a single time. We're seeing it as spread out in time. So we see 2 trillion, but really today, most of those 2 trillion have combined together to form 20 times fewer galaxies. So there you go. So we were right and wrong at the same time, which is always nice.
Question down here in the front, on the left.
That was a really good question, though. And yours was too. I don't
Keep
mean
your hand up.
by it.
Hey, Lawrence. What are your thoughts on the EM drive, or the M drive, produced by...
Yeah,
NASA?
people ask about this all the time. This is using the vacuum to somehow get energy. And NASA's talked about this. And as I was saying to someone else the other day, NASA doesn't know its ass from a hole in the ground when it comes to fundamental physics. I mean, really. It embarrasses me and offends me because NASA's great at engineering and making rockets, and that's what it should be doing. But the point is, you can't mine the vacuum and get energy. Now, it is true that empty space has energy. That was one of the things I proposed and was discovered. Empty space has energy. So why not use it? Well, the answer is, we think, okay, that the energy of empty space is what we call the ground state energy, the energy of the vacuum. Now, what does that mean? The vacuum in physics is the lowest energy state. Okay, the lowest energy state. So for at least on this table, the lowest energy state is for this pitcher to be on the table. Okay, it's got more energy when I put, and I can get energy out of it by letting it go, but I'm not going to do it. Okay. Now, so the vacuum, we think, the vacuum is defined to be the lowest energy state in nature. Now, it has non-zero energy. But if you could extract energy from it, there'd be another state that's lower energy. You cannot mine the vacuum. It's just simple as that. And NASA has explored that, and I've been to NASA. You know, I wrote a book on the physics of Star Trek, and there was a group there that wanted to build a warp drive. And I remember going into the meeting, and there were all these models of the USS Enterprise there, and all these engineers were really excited. And the point is, it's true, I wrote, you know, warp drive might be possible in principle, but we don't know, given the laws of physics, but it might be possible. But it's not an engineering problem. It's not something where you're going to tinker and, you know, and somehow, suddenly, it's fundamental physics. And so, you know, there are new ways of going faster than we can go, and NASA's looking at some of them. I'm involved in one. It's called Breakthrough Starshot. So my friend Stephen Hawking is on the same committee. And we were talking about developing a device that will travel at 20% the speed of light to get to Alpha Centauri in 20 years. That may be possible. Maybe. It's on the edge. Okay? But, so there are lots of interesting ideas you can do. But mining the vacuum for energy, if anyone talks to you about that, don't listen. If anyone asks you to invest in it, don't invest.
Question there? Come to you in a minute.
Thank you very much. My question is this. So your theory is before the Higgs field.
Yeah.
Is there an experiment you can run now to still prove them?
To still prove my ideas are right?
Yeah.
Well, I haven't given up. And in fact, but I'm in the process of actually working on a paper to see if there's any way that the Higgs could be an illusion. And I'm still, you know, I think it's worth exploring. You know, the more we explore, the more difficult it is, but I haven't given up yet. And it's important not to give up. But it's also, I'll be happy to be wrong, and I'll be happier to be right, because this time, maybe the Nobel Committee will do the right thing. And no, anyway, it doesn't really matter. You got the point. It has to make a prediction that somehow, if it's exactly the same as what we see, then it's kind of a useless theory, right? It has to be able to predict something different, some new observation that's different, because if you can't falsify it, it really isn't good science. So I could maybe make a theory that reproduces everything we could see that somehow has, you know, wheels within wheels, you know. But if it doesn't predict something else you can see, then the simplest theory is just as good. And so you really have to look for something new, and that's what we've been looking at. But the likelihood is most theories are wrong. Almost all theories are wrong. And by wrong, I mean that they don't agree with nature. And if it wasn't that way, anyone could do it. And I've created beautiful theories in my life, and nature just hasn't been smart enough to adopt them. That's all.
By the way, I really like the attitude of working at overturning the Higgs findings, because it gives us hope on Trump and Brexit. You know? Is somebody over there?
I don't know which will be easier.
Have you got a mic?
Trump hasn't been elected yet. I keep reminding people. Just remember,
we haven't left the EU
5
yet,
days for now. So there's still time. Anyway, yes.
So when you spoke briefly about infinity, you said...
Could you stand up so Lawrence could see you?
And I can maybe hear you better.
Yeah. So when you spoke about infinity, you said it was a bit crazy and physicists didn't really like it. So my question is the universe itself infinite?
Is the universe infinite? Oh, good question. We don't like infinities. And the answer is we don't know if the universe is infinite. The best picture is, I think, based on what we our current ideas, which are tentative, and I wrote about in the last book, is that it's not. It's just very, very, very big. I think what's his name said that in the Hitchhiker's Guide to the Galaxy. It's so big it makes going to the chemist look like nothing. But it's very big but finite. Okay, so that gets. But it turns out you don't get so that solves that problem. But it doesn't. It comes at a cost. Our universe may be finite, but there's a possibility that there are an infinite number of universes. And if there are, things are very, very strange, because then those weird things that infinity makes possible are suddenly possible. Because if there are an infinite number of universes, then everything is repeated. Or not repeated, but if there are an infinite number of universes, then this lecture will happen exactly the same, except a few words will be different, in another universe. But not just once, an infinite number of times. And then there'll be an infinite number of universes in which I'm sitting there and you're up here, and so it's really disgusting. and not that you're up here, I'd be happy, but no, well, I prefer up here, I guess. But so these are problems that physicists are actually dealing with. Because if there are an infinite number of universes, then probabilistic arguments tend to go out the window. But the good news is, it's most likely that our universe is finite, if that makes, and that's at least easier for many of us to comprehend. But the universe doesn't really care what we like, and so we'll just have to find out. And there may be ways of testing, as I have talked about in another lecture recently. We may actually be able to test for the existence of other universes, which I didn't think was possible 4 years ago when I wrote A Universe from Nothing. So there's great progress that we may be in the midst of making. It has to do with gravitational waves.
I spotted you two guys. It was going to be you with galaxies on your tie, but somebody's got the mic before you, so we'll come to you second.
Okay, we'll come next. Okay, we'll do that, and then I guess you.
Yeah.
Hi. So what are your thoughts on quantum entanglement, and can it be used for transferring information faster than the speed of light?
Ah, good. And by the way, it's the DNA. I don't think it's galaxies. But
Is that
anyway,
DNA,
but
is it?
anyway, so okay, it looks like quantum mechanics allows information to be transferred faster than light. Once again, a cosmic catch-22. It can't be. So it is true, and this bothered Einstein. One of the many reasons he didn't buy quantum mechanics, because of this spooky action at a distance, as he called it. It is true that I can do what's called entanglement. I can entangle two particles, like two electrons or two photons, create them in a very special quantum mechanical state, and then I can separate them from here to Alpha Centauri. And then let's say I take two electrons and I create them in a state so one is spin up and one is spin down. Actually, they have opposite spins. It turns out they're spinning in all directions at the same time. Okay? But they're opposite. Whatever. At the same time, they're spinning in all directions, but they have opposite directions. And I move them here. Now I measure this one, and I find out it's spinning over here. It immediately makes this one spin that way. Or at least that one will be measured to be spinning that way. Immediately. So, isn't that information traveling faster than light? I mean, it's not. It's instantaneous. I do this measurement here. Instantaneously, that other one collapses into that state. Before I made the measurement, they were both spinning in all directions at the same time. I measure this one, suddenly, boom, I find it's that direction. That makes this one go in that direction. Well, it sounds like information faster than light, but it turns out it's not. And no information is transferred in that. Okay. So how can you do this? Well, so if I have an experimenter here, and he measures it here, an experimenter here will measure that electron to be that way. Okay? But let's take 100 electrons. Okay? So if I measure 100 electrons, 50% of the time I'll find this one electron to be spinning that way, and 50% of the time I'll find it spinning that way, according to the laws of quantum mechanics. Okay? What will this experimenter measure? 50% of the time it'll be pointing down, 50% of the time it'll be pointing up. There's no experiment that this experimenter can do that will tell him that this measurement's been made. The only way to know is if this experimenter phones that experimenter and then says, the next electron you measure will be spinning down. And that's true, but that happens at the speed of light. So no information is transferred faster than light, even though, so, you know, the universe is just, you know, the way it is. And it's, okay.
Gentleman there.
Hi. The question from the front row reminded me of something.
We're going there and there. We did promise him after that. Okay, sorry, go on.
Yeah, I mean, could you tell me what you think of the alternatives to inflationary theories like high speed of light in the early universe.
Oh, yeah, okay.
And
Inflation
what is the problem that these models are trying to solve?
Well, people have, look, inflation is an idea which I could have talked about in a longer lecture here, and I certainly have in the last book. It turns out we have every reason to believe that there was a really big energy in empty space early on in the history of the universe. When the universe was a billionth of a billionth of a billionth of a billionth of a second old, it expanded very fast, increasing its volume by a factor of 10 to the 90th in a billionth of a billionth of a billionth of a billionth of a second, going from the size of an atom to the size of a soccer ball in an instant. And it turns out our ideas of particle physics tell us that that's plausible, but more importantly, it actually resolves all the problems of our visible universe. It really explains why the universe looks the way it does. So we think it's plausible. You might say if it explains why the universe is the way it is, then we've tested it and we know what happened. But that's not true, because while inflation explains everything we see, it turns out the idea of inflation is so malleable that if everything we see was different, inflation could explain that too. And as I said before, that's not a good physical theory. So inflation is an idea right now. It's the best idea we have. But of course, people are saying, well, it's just an idea. Maybe there are other alternatives. Some of those alternatives are stranger than others. One that's not so strange is that maybe the speed of light changes, and that explains our property. It turns out it's a really silly idea. I mean, in a sense, not silly, I shouldn't say that. But first of all, we know, well, it's silly because experimentally we can actually test, back to when the universe was far less than a second old, that the speed of light hasn't changed. Okay? So somehow it would only have to change very early on and then stop changing. We can measure to an accuracy of better than 1 part in 100,000 that the speed of light was the same in the early universe that it is now. It's amazing you can do that, but we can do that. But more importantly, there's no theoretical reason why the speed of light should change, because it really would mean the fundamental laws of electromagnetism would have to change, because the speed of light is based on those. And it's much more radical an assumption than inflation, because inflation happens naturally, given essentially the laws of physics we now understand. And so you have to it's far more radical than inflation. In fact, as my friend Frank Wilczek would say, inflation is radically conservative, in the sense that it's pretty well the simplest idea that explains everything we see. And these other ideas are much more Baroque. Does that mean they're wrong? No, but they're much less well motivated. Okay? And they're unnecessary at this point, because the physics that we know of, with very little modification, can explain everything we see. So there isn't really the need for those modifications. Again, that doesn't mean they're not there, but it just means that if you're a betting person, you'd say that they're not necessary, and they're probably not there then. But, you know, the only way is to find out. Yes?
I want to ask you, is time real? Or is time real? Or is it just a concept?
I think it's real, because we're going to end in a few minutes. And if I look at that clock, and it certainly is real in the sense that you feel differently now than you did an hour and a half ago, and better or worse, I can't say. So it's time is real, but the point is that people don't ask, is space real? And time and space are tied together by relativity, and even more so by general relativity. So time, in some sense, is as real as space. Now, it is true that perceptions of space and perceptions of time are relative. So in that sense, neither is real, but there is some. But they are the playing field on which things happen. Space and time are the playing field on which events occur. And if that playing field didn't exist, the events wouldn't occur. The characteristics of the events depend upon the nature of the playing field. As I often say, if a cricket stadium were 10 times bigger, it'd be 10 times more boring. And if such a thing is possible. So they are the parameters that we use to describe the universe. They have. So I don't know what when people talk about reality, I don't really know what that means, in the sense that space clearly exists. We measure it to exist. Time clearly exists. We measure it to exist. My watch ticks, and so but it is true that those are facets of our accident of our existence, just like the Higgs field. But I don't think that doesn't make them real. It just means that we have a myopic view. So our experience of time our experience of time through our consciousness may be myopic and artificial. And that may be true. But that's outside my pay grade. I mean, seriously, because when you start talking about consciousness, you're talking about stuff that nobody understands, no matter all those books. Someone once said there's so many books on consciousness because no one understands it. You only need one book on gravity, okay? And so it's, maybe we'll find that out. But those are questions that I don't think that really aren't essential for physicists to worry about, because we use the concepts of space and time to make predictions that work. So I can make a prediction about time, that if I take a gun and shoot you, that something will happen in the future. And that prediction will be accurate. And that's all that science doesn't try to do anything more than that.
This is going to have to be the last question, I'm afraid. Have you got the mic?
Okay.
This gentleman here, stick your hand up so we can see where to bring the mic. Thanks.
Interesting stuff.
Oh, thank you.
Obviously, as you alluded to, there's a lot of people who don't quite get it, probably me included.
Oh, well, none of us quite get it. That's what's so fun. Yeah.
And a lot of people need education. What can we do to educate people?
What?
A lot of people need education there.
Oh, what do we do to educate people? Well, I wish I had a silver bullet. I mean, I try. I think what we need to do is first excite people. And one of the ways we don't do that, as I say, is we teach physics as if it's done by dead white men 100 years ago or 200 years ago. There are many outstanding problems to be solved. And you can understand those outstanding problems without knowing everything. I mean, you can understand what the problems are. And I was using a quote, which is in one of my books, which is from Louise Bogan, which says something like the greatest part of any mystery is the starting point. And so we can bring people to the starting point so they get excited. But we do that, it seems to me, in a way that's the opposite of the way we educate people, which is because of the accident of history, we tend to treat schools as sources of information, as sources of answers. What they really should be is sources of questions. If you have one of these, you can get a lot of information and misinformation. What we need to do is encourage kids to ask questions and then work with them and be willing to say, I don't know the answer. Parents need to do this. Teachers need to do this, to say, I don't know the answer, but let's see if we can find out the answer. So it's a voyage of discovery. It's not ramming things down people's heads, because that's boring for everyone. And so what we need to do is educate, especially now, is educate children to question, but also, equally important, to learn how to proceed to a logical way to try and get answers. And Anthony's nodding because he'd say that's what philosophy is in some sense. And he's right. But the point is that we particularly need to teach kids how to filter information, because there's lots of stuff here. And you need to know how to tell the wheat from the chaff. And that process is a scientific process, the skeptical process, scientific skepticism, not accepting things on faith, questioning and demanding evidence. So the process of questioning and the process of learning how to the answer, that's what we need to teach in school, and the rest will come, because most of what you learn in life you don't learn in school, and so it's not as if you're going to get all the answers. So that's my little prescription, and I wish, anyway, that's my prescription.
Well, I'm 100% with Lawrence on that one. You may know, if you've done your homework on Lawrence, that he's the foundation professor at the University of Arizona, heads up an institute called the Origins Institute, has a very, very modest remit. They're just investigating the origins of the universe and life, so that's...
and everything. Life, the universe, and everything.
Okay. After the election in the States, in fact, the very next day, I got a message from Lawrence asking for a job over here, but I was busy. I was busy packing to leave because of Brexit.
We were going to switch.
So all I can say is I'm pretty sure Lawrence is not going to feel that much at home in the US in the next few years if the Electoral College doesn't do what he wants it to do. But at least he's at home in the universe. And thank you very much indeed to Lawrence. You always go really good. Thanks, everybody.
And so the science, certainly the experience you'd have, is that it was natural, ingrained, that a very central property of your existence was the fact that this direction was special. And religions would be based on that somehow that direction was ordained by God and designed so that you could live in the world in which you're living. And the point is, this is an illusion. And it's an illusion we can see because we're outside of that system. Wouldn't it be amazing if scientists on that crystal could somehow divine that the real world was quite different than the world they see? And that's the story I want to tell you about, the revolution that's really taken place over the last century in our fundamental understanding of the universe, of matter and energy on its smallest scales, that has revealed this illusion that we have, but also revealed that things that we hold dear, including our very existence, are an accident. That the illusion of design, among other things, as you'll see, is an accident. So that's where I want to go, and that's a story I want to tell, and I do think it's the greatest intellectual journey that humans have ever taken. And it saddens me that it's not more well understood, and I'm very happy to have written the last book about it, because many people think of the 20th century revolutions that have taken place, Einstein and quantum mechanics, but there's actually a period much more recently where, in fact, I think in the far future, when people look back, they'll say the most revolutionary period of the 20th century was not 1905, was not in the 1920s, but actually was much later. But that isn't well known, and I want to relate it to you now. Okay. This is our universe, as seen in a rather grainy image right now. But this is the deep Hubble Deep Field image, and we already know that a lot of my last book, in some sense, was about the fact that this image, in some sense, on the larger scales, is sort of an illusion. That the important image, Picasso famously said that he painted what he saw, and obviously lied. But you know, Van Gogh was kind of unstable. And so the question is this what he saw, or is this the hidden reality that he saw was underneath? When he looked at the sky, this is what he felt was underneath. It's that hidden reality, which is the title of this lecture, that is interesting to me, because we're hardwired to want there to be more to the universe than we can see. And science has certainly provided fodder for that. The science has discovered a world that many aspects of the world we can't see, some of which I'll talk about. It's also been responsible for religion. But it's this notion that there really is that there's a tip of a cosmic iceberg that we're somehow seeing. And the question I have is, what if this is what he really saw? Okay? What if the world was an illusion? What if the world we really see now is an illusion? And that's the subject I want to talk about, because it really is. The world we see is an illusion. And a better example of that is this image, which I'll come back to, which is icicles on a window, which you may, again, get cold enough someday here to have, although not if Donald Trump has anything to do with it. But so they're beautiful, and it's interesting to look at this pattern on a window. But when you do, you notice that the crystals are in all different directions. There's nothing particularly special about them. But ask yourself, what if you lived on one of these ice crystals? What if you lived on this one right here? What if you're a physicist living on this ice crystal? What would the world seem like to you? Well, it would be obvious, first of all, there's one direction that's very special. That direction there. And the laws of nature would be very different in that direction than they would be perpendicular to that line. Stuff is not the stuff we see, but the stuff we can't see. And that really dominates the universe. And in fact, I've lectured in this very hall, about that subject. But I want to go back to say, well, when we look at this universe, it inspires us to think about what caused all this. And I go back, and it's not just because my friend Anthony Grayling introduced me that I want to begin with philosophy. But as many of you know, I'm a great lover of philosophy. And I begin with this fellow. And whenever I ask who this is, and I'm not going to do this because I don't want to embarrass you. Everyone always says Aristotle, and it isn't. Okay, it's Plato. And for me, Plato was profoundly important because I was forced to read him when I was in high school. I grew up in Canada where they educate you, and so I read Plato's Republic, and there was a part of the Republic which has stayed with me ever since, the allegory of the cave, and so I went back to my high school book and I found a drawing from it, which is this. So Plato argued that we are, in fact, reality is not what we see. What we see is a shadow of reality. And he used this example of a cave. He likened humans to being individuals in a cave, chained to a cave, so they could only see the walls of the cave. And outside was here, and the light from outside came back, and also there was a fire behind them, and they could see people on this roadway, but they could only see the shadows. So their world was just a shadow of reality. And he said, well, you know, the job of the philosopher, mathematician, is to discern, based on those shadows, what reality really is. The job of modern physicists, say. And he said that if you that you could try.
Evening, ladies and gentlemen. Welcome to the Moncure Conway Memorial Lecture. These lectures have been going on since 1910, with not many interruptions. There were a couple during the Second World War, although in fact there were occasions on which lectures were held here. You'd be very pleased to know that during the course of one of them, a bombing raid occurred, and a local church nearby was bombed, but not Conway Hall. Well, it's been a series of lectures by some amazingly distinguished people in the past. Bertrand Russell, A.J. Ayer, you name them really, they've been here and lectured here. So these walls have heard some interesting things. And we have the very, very great pleasure tonight indeed to have my good friend, Lawrence Krauss, very distinguished physicist, a great communicator about physics, somebody who's done very important work in physics. You will know, those of you who have done your homework on Lawrence or have been avid readers of his for some time, that he was one of the theoreticians who spotted that there might be dark matter and energy in the universe. And then some folks later on went and made the observations and got the Nobel Prize for it, but they wouldn't have got it if it hadn't been for Lawrence. And Lawrence is still active, still working, still busy in physics itself, but also busy as an activist. At the moment, he's trying to bring down Donald Trump before Donald Trump gets up. But he is an indefatigable communicator about this very, very great adventure, the greatest adventure, really, of humankind, which is the natural sciences, our understanding of the structure and properties of the material universe. And here's somebody who knows something about it, and he's going to tell us something about it right now. And by the way, this introduces Lawrence's very latest book, not yet out on the shelves, but it soon will be, and he'll tell you about it in a minute. Lawrence Krauss.
Thank you. Thank you. Thanks. It is a pleasure to be back here, and it's an honor to be doing this lecture. It indeed has had a distinguished history. As I was telling Anthony, they ran out of the distinguished people, and now they had to go for a physicist like me. But I put this up. I'll come back to it. But the title of this story, which is the title of my new book, is The Greatest Story Ever Told So Far. And so I thought I'd begin as a good storyteller might, in fact, a good British storyteller. So I figured it's the best of times, and by that I mean that the Large Hadron Collider is operating and has not created a black hole that would destroy the world. But it is indeed also the worst of times, well, let's get rid of him, but, okay. And what is, I put this up because, you know, one of the things that physics lectures do take us away from the myopic crap that we have to deal with. But also what I want to talk about is really the greatest intellectual adventure that humans have ever taken, and in some sense the greatest aspects of being a human. So this is the worst aspects of being a human, and it's so nice that we can periodically rise above that the awful experiences I'm having right now, and we are, and you will. Anyway, so let's go now back to the picture I started with, which is Van Gogh's Starry Night, which is one of my favorite images of his. When I look at this, I wonder what he was thinking when he painted it, because did he really see this